Hey guys, how's it going? In the last episode, we talked about 4-bar mechanisms. These mechanisms are able to use it in all of these competitions from starter all the way to premiere. Together with this episode where we will be talking about sliders and elevators. These two mechanisms will most likely be useful for your robot. For example, in this year's challenge competition, teams are required to hang flags at the top of the post. Alternatively, you can use a stick to hang or with a more advanced overkill telescoping slider mechanism. Now you might be wondering, what is a telescopic elevator design? It is a mechanism that allows robot to carry items from point A to B in a linear form. Telescopic means a section of the tubing are sliding into one another. Telescopic elevators are more compact and lightweight compared to standard elevator designs. Usually, as in standard design, larger tubing will be on the lower end. This will create a section that are wasted. For this design that I'm working on, the smaller end will be at the bottom, allowing us to design a slider block that can travel the full potential distance from ground up, hence named Inverted Telescopic Elevator Slider Design.
Movie magic! Movie magic!
As we know, our robot do have weight limits, so in this video I'll try to design the slider mechanism as light as possible. For my design, the shaft we are using are MakeX dimensions, which is 4mm in diameter, pairing with the bearing that are 4x10mm. Please work. Yes! Yes! We can also use 4x8 bearings, but all the fitting will be extremely compact. The clearing between the outer shaft to the outer bearing radius is only 2mm, which will make installing and manufacturing extremely complicated. Anything bigger than 4x10, the bearing will be too heavy. We can also try ceramic bearings for weight reduction, but further testing will be needed. For further implementations on weight reduction, we can use aluminum shafts. It will be at least 1/3 of the weight, but the only downside we faced in the past, our aluminum shaft diameter will be greater after manufacturing, which will make installing bearing quite challenging. Further machining or sanding will be required. For the shaft I use are pre-cut into desired length. This will require much less manufacturing in the workshop, and all the shafts are clean and chamfered and smooth and nice and accurate. For the 3D printer slider housing, I went through 5 different iterations, including changing the gap between the bearing and the tubing, reducing structural materials, added adjustable bearings, and so on. I can also chamfer the edges and have smoother finish, but I ran out of materials. I don't want to open new filament because I'm pushing damage. The constant force spring I use are 0.8 kilograms, 5mm wide, and 600mm long. We like to use force springs because compared to the normal spring, the forces will increase when stretched to a certain length. But for force springs, it will provide constant force at any positions. And also for the dimensions, it is more compact compared to standard springs, which makes our slider design more compact. But the quality I got is poo-poo. So when it stretches out, it curves a little, rubbing the inner wall, and it's not smooth. It is not smooth, but I'm pretty sure the concept and design is fine.
Fine, but isn't it nice?
For tubing selections, I went to our local material shop to pick out box tubings that are suitable for my design. I selected these standard parts, including shafts, bearings, and tubes first because if you're designing the 3D printed mechanism first, tubing dimensions you design may not have it in the standardized units. If you were going to purchase something that is not standardized, such as tubes, bearings, sheet metal, it may increase the cost because manufacturers need to tailor to your need. After getting all the standardized parts, now you can start CADing the mechanism. Designing anything in the first version may be challenging. There are a lot of unknown factors that can't be seen when building the first mechanism, and this is where trial and error comes in. We went through lots of different past versions of the slider from MakeX to FRC competitions, and these parts have been used by us in many different occasions. For us, the outer diameter of box tubing are 25 by 25 and 30 by 30 millimeters. All of them are 1 millimeter thick. These tubings are extremely lightweight and can be brittle. When applied pressure in the center of the tubing, it can buckle. Therefore, when designing the slider blocks, all the bearings that are contacting the beam are traveling on the edge of the box tubing. Because the force spring is not working, theoretically the speed should be similar to a slider with no load because weight cancels out with the force spring. Since not working, it's a bit slower than I wanted to. For accurate movement, I chose Dyneema rope. This kind of rope is commonly used in fishing, sports equipment, and other rigging applications. Compared to polyester, the tension deformation stretches 0.024% less than Dyneema. At full load, the elongation is at 3.5%. That's a 35 centimeter difference between these two ropes and 15 meters.
Ooh, tight.
This design have went through many different iterations and still have rooms to improve. If teams are interested, I can do a part 2 of this design and share all the drawings and parts I use in this video. And that would be it for this episode. Once again, thanks for watching all the way till the end. In the next video, we'll be looking into a ball sorting design. If you liked it, you can subscribe if you want, share with your friends and teams, and good luck to all the teams at UAE Regional. If you have any further questions, follow me on Instagram and I'll try my best to reply to all of them. And until next time, goodbye. So